Right now, 7,500 light-years away from Earth, there's a star so massive and unstable that it could explode at any moment with the force of 10 billion suns. Eta Carinae, a hypergiant star system in the southern constellation Carina, has been teetering on the edge of catastrophic collapse for over a century, and Stephen Hawking's analysis revealed that when it finally detonates, the resulting gamma-ray burst could strip away Earth's ozone layer and trigger a mass extinction event that makes the dinosaur-killing asteroid look like a minor inconvenience. This isn't some distant theoretical threat that might happen in millions of years. Eta Carinae is what astronomers call a luminous blue variable, a type of star so unstable that it can explode without warning, and when it does, it will become one of the most powerful events in the known universe. The star has already shown signs of extreme instability, experiencing massive eruptions that have made it one of the brightest objects in the southern sky. Stephen Hawking spent years studying hypergiant explosions and their potential effects on planetary atmospheres, and his calculations revealed something terrifying. If Eta Carinae explodes as a hypernova and directs its gamma-ray burst toward Earth, the radiation could arrive here in just 7,500 years, but the effects would be instantaneous and devastating when they hit. We're talking about a cosmic death ray, powerful enough to sterilize half the planet in seconds. What if I told you that this stellar monster has already begun its death throes, that astronomers have detected warning signs suggesting the explosion could happen within our lifetimes, and that there's absolutely nothing we can do to stop it or protect ourselves from its effects? Hawking's research suggests that Eta Carinae represents the kind of cosmic threat that could end human civilization in an instant, without warning, and without any possibility of defense. This is the story of the most dangerous star in our galaxy, why it's primed to explode, and what Stephen Hawking discovered about the terrifying consequences when it finally does. Before we explore Stephen Hawking's analysis of Eta Carinae and why this stellar time bomb could trigger Earth's next mass extinction, make sure to hit that subscribe button because we're about to uncover the most immediate cosmic threat that could end life as we know it. Stephen Hawking's fascination with Eta Carinae began when he realized that this stellar system represents everything dangerous about massive star evolution compressed into a single, observable object. Located in the Carina Nebula, Eta Carinae isn't just one star. It's a binary system containing two of the most massive stars ever discovered, with the primary star weighing in at over 150 times the mass of our Sun. The physicist understood that stars of this magnitude exist at the absolute limit of stellar stability. They burn through their nuclear fuel at such enormous rates that their lifespans are measured in millions of years rather than billions, and they spend their entire existence fighting a losing battle between the outward pressure of nuclear fusion and the inward pull of their own gravity. When that battle finally ends, the result is one of the most violent events in the universe. Hawking's analysis of Eta Carinae's observational history revealed a pattern of behavior that he found deeply disturbing. In 1843, the star system underwent what astronomers call the Great Eruption, an explosion so massive that it briefly became the second brightest star in Earth's sky and ejected material equivalent to several solar masses into space. For nearly 2 decades, Eta Carinae remained one of the brightest stars visible from Earth's southern hemisphere. But this wasn't a supernova. It was something far more ominous. The physicist realized that the Great Eruption was likely a false supernova, a massive instability event that occurs when hypergiant stars approach the final stages of their evolution. These events are warning signs that the star is preparing for its ultimate collapse, and they can occur repeatedly over periods of decades or centuries before the final explosion. The physicist's calculations revealed that Eta Carinae's Great Eruption ejected enough material to create the distinctive homunculus nebula that now surrounds the star system. 2 massive lobes of gas and dust expanding outward at speeds of over 600 kilometers per second. This nebula isn't just beautiful, it's evidence of the incredible violence that occurs when hypergiant stars become unstable. More disturbing was Hawking's analysis of what the Great Eruption tells us about Eta Carinae's current state. The physicist calculated that stars experiencing such massive instability events are typically within a few thousand years of final collapse, an instant in cosmic terms. The fact that we witnessed this eruption just 180 years ago suggests that Eta Carinae could explode at any moment. The physicist also studied the star's more recent behavior and found additional warning signs that the final explosion might be imminent. Since 1998, Eta Carinae has been brightening steadily, and its spectrum has shown dramatic changes that suggest fundamental alterations in the star's internal structure. These changes match theoretical predictions for the final stages of hypergiant evolution. Think about the implications of this timeline. We're not talking about a threat that might materialize in millions of years. We're discussing a star that showed signs of extreme instability within recorded human history and continues to exhibit behavior suggesting imminent collapse. Eta Carinae could explode tonight, next year, or within the next few centuries, and we would have no advance warning. Hawking's analysis of hypernova explosions revealed why Eta Carinae represents such an unprecedented threat to life on Earth. When hypergiant stars collapse, they don't just explode. They create what physicists call collapsar events that can produce gamma-ray bursts, the most energetic phenomena in the known universe. A single gamma-ray burst releases more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. The physicist calculated that if Eta Carinae explodes as a hypernova and produces a gamma-ray burst pointed toward Earth, the radiation would arrive here traveling at the speed of light with an intensity that could fundamentally alter our planet's atmosphere and biosphere. We're not talking about gradual climate change. We're discussing instantaneous atmospheric destruction that could make Earth uninhabitable within hours. The gamma-ray burst from Eta Carinae would first strike Earth's upper atmosphere, where the intense radiation would interact with oxygen and nitrogen molecules to create massive amounts of nitrogen dioxide. This chemical reaction would rapidly destroy the ozone layer that protects life on Earth from harmful ultraviolet radiation from the Sun. Hawking's atmospheric models showed that a direct gamma-ray burst from Eta Carinae could destroy up to 75% of Earth's ozone layer within seconds of arrival. The loss of ozone protection would expose the planet's surface to lethal levels of ultraviolet radiation, causing immediate damage to DNA in all living organisms and triggering widespread ecosystem collapse. But the ozone destruction would be just the beginning. The physicists' calculations revealed that the nitrogen dioxide created by gamma-ray interactions would form a thick, reddish-brown layer in the upper atmosphere that would block significant amounts of sunlight from reaching Earth's surface. This gamma-ray winter effect could reduce global temperatures by several degrees and disrupt photosynthesis worldwide. The physicist also analyzed how the intense electromagnetic pulse from a gamma-ray burst would affect Earth's technological infrastructure. The burst would induce massive electrical currents in all conducting materials on Earth's surface, potentially destroying power grids, communication systems, and electronic devices across entire continents. Modern civilization could be knocked back to pre-industrial technology levels in an instant. Let me ask you something that might fundamentally change how you think about cosmic threats. If we know that a specific star has the power to end human civilization instantly, and if that star is showing signs of imminent explosion, shouldn't we be treating this as the ultimate existential risk? Share your thoughts in the comments below, because this might be the most underestimated threat facing humanity. Hawking's research into the directionality of gamma-ray bursts revealed both reassuring and terrifying aspects of the Eta Carinae threat. Gamma-ray bursts are highly directional phenomena. They shoot out in narrow beams from the poles of collapsing stars rather than radiating equally in all directions. This means that most hypernova explosions pose no threat to distant planets because their gamma-ray beams point away from them. However, the physicists' analysis of Eta Carinae's orientation relative to Earth showed that we might not be so fortunate. The star system's rotational axis appears to be aligned within about 45 degrees of Earth's direction, placing us within the potential cone of destruction if the star produces a gamma-ray burst. While this doesn't guarantee that a burst would hit Earth directly, it means we cannot rule out the possibility. The uncertainty in Eta Carinae's exact orientation creates what Hawking called directional ambiguity. We know enough to be concerned, but not enough to be certain of our safety. The star's massive surrounding nebula makes precise measurements of its rotational axis extremely difficult, leaving us with probability estimates rather than definitive answers about our vulnerability. More disturbing was the physicists' discovery that binary star systems like Eta Carinae can produce even more dangerous explosions than single stars. When two massive stars orbit each other closely, their gravitational interactions can accelerate the evolution of both stars and create more violent collapse scenarios. The physicist calculated that binary hypernovae can produce gamma-ray bursts up to 10 times more powerful than single-star explosions. Hawking also explored how the unique characteristics of the Eta Carinae system might affect the nature of its eventual explosion. The two massive stars in the system are gradually spiraling closer together, and the physicists' models suggested that they might eventually merge before either star explodes individually. Such a merger would create a hypermassive object that would collapse almost immediately into a black hole while producing an extraordinarily powerful gamma-ray burst. The physicists' timeline analysis for this merger scenario was particularly unsettling. Based on the observed orbital decay of the two stars, Hawking calculated that they could merge within the next few thousand years, an extremely short time in astronomical terms. The merger would be preceded by increasingly violent interactions between the stars, creating a series of massive eruptions that would serve as warnings of the approaching catastrophe. Recent observations of Eta Carinae have revealed additional disturbing developments that support Hawking's most pessimistic predictions. X-ray observations show that the interaction between the two stars is becoming increasingly violent, with massive amounts of material being stripped from both stars and accelerated to near-light speeds. These interactions are exactly what theoretical models predict should occur in the final stages before stellar merger or collapse. The physicist also analyzed how the stars surrounding nebula might affect the propagation of gamma-ray bursts. Normally, the dense material around hypergiant stars can absorb some of the gamma radiation from stellar explosions, reducing the threat to distant planets. However, Hawking's calculations showed that Eta Carinae's nebula has a complex bipolar structure that might actually focus gamma radiation into more concentrated beams. This focusing effect could make Eta Carinae's eventual gamma ray burst even more dangerous than typical hypernova explosions. Instead of a diffuse burst that spreads its energy over a wide area, the star's nebula might concentrate the gamma radiation into narrow, extremely intense beams that could cause more severe damage to any planets they encounter. Hawking's analysis of historical mass extinction events revealed disturbing correlations between gamma-ray burst timing and major die-offs in Earth's fossil record. The physicist found that several of the most severe extinction events in Earth's history, including the Ordovician extinction that eliminated 85% of marine species, occurred at times when nearby stars were likely experiencing hypernova explosions. While these correlations don't prove that gamma-ray bursts caused past extinctions, they suggest that such events are capable of triggering global catastrophes that persist for millions of years. The physicists' models showed that even a relatively weak gamma-ray burst could initiate cascading environmental changes that would fundamentally alter Earth's climate and ecosystems. The physicist also explored how modern life on Earth might be particularly vulnerable to gamma-ray burst effects. Unlike past extinction events that primarily affected marine life, a gamma-ray burst today would strike a planet dominated by land-based ecosystems that depend heavily on atmospheric protection from solar radiation. The loss of ozone protection would be particularly devastating to plants and animals that have evolved under stable atmospheric conditions. More ominously, Hawking calculated that human technological civilization might be especially vulnerable to gamma-ray burst effects. Our dependence on electronic technology, global communication networks, and satellite systems create single points of failure that could cripple modern society, even if the biological effects of the burst were survivable. The physicists' analysis of potential survival strategies revealed the sobering reality that there might be no effective defense against a gamma-ray burst from Eta Carinae. Unlike asteroid impacts or volcanic eruptions, gamma-ray bursts arrive without warning at the speed of light, giving no time for preparation or protection. Any defensive measures would need to be in place continuously, just in case the burst occurs. Hawking explored various theoretical protection scenarios, from underground shelters to atmospheric engineering projects designed to rapidly restore ozone protection. However, his calculations showed that the scale of infrastructure required for meaningful protection would be beyond current human capabilities, and the warning time available would be insufficient to implement such measures. The physicist also considered whether space-based civilization might offer better survival prospects than remaining on Earth's surface. Orbital habitats and lunar colonies would be even more vulnerable to gamma-ray radiation than Earth's surface, lacking any atmospheric protection whatsoever. Mars colonies might fare slightly better due to the planet's thin atmosphere, but would still face lethal radiation levels. Perhaps most disturbing was Hawking's analysis of the long-term consequences of a gamma-ray burst impact. Even if some humans survived the initial radiation and atmospheric effects, the physicist's models suggested that the resulting environmental changes could persist for thousands of years. Recovery of technological civilization might be impossible if the burst destroyed critical infrastructure and reduced the human population below sustainable levels. The physicist understood that the Eta Carinae threat represents a fundamental challenge to human survival planning. Most existential risks that we prepare for, nuclear war, climate change, asteroid impacts, develop over timescales that allow for preparation and response. Gamma-ray bursts occur instantaneously and without warning, making traditional risk mitigation strategies ineffective. Hawking's research suggested that the best approach to the Eta Carinae threat might be to accelerate human expansion beyond Earth while we still have time. Establishing self-sufficient colonies on multiple worlds would ensure that human civilization could survive even if Earth were sterilized by a gamma-ray burst. However, such expansion would need to occur within the next few centuries to be effective. The physicist also explored how knowledge of the Eta Carinae threat should influence human priorities and resource allocation. If there's a significant probability that human civilization could be destroyed by a stellar explosion within the next few thousand years, should we be focusing more resources on space colonization and less on terrestrial concerns? Recent developments in gamma-ray burst astronomy have only reinforced Hawking's concerns about the Eta Carinae threat. New observations have revealed that gamma-ray bursts are more common and more powerful than previously thought, and that hypergiant stars like Eta Carinae are particularly prone to producing the most dangerous types of bursts. The physicist's final analysis of the Eta Carinae threat painted a picture of humanity living under a cosmic sword of Damocles, a stellar time bomb that could explode at any moment and end our civilization without warning. We know the threat exists. We understand its magnitude, but we have no way to predict when it will occur or defend ourselves when it does. Hawking understood that this situation represents a fundamental test of human wisdom and priorities. The Eta Carinae threat forces us to confront the reality that our existence is far more precarious than we typically acknowledge, and that cosmic forces beyond our control could end human civilization regardless of our terrestrial achievements. The physicist's research suggested that awareness of cosmic threats like Eta Carinae should fundamentally change how we approach human survival and expansion. We cannot control the stars, but we can control how we prepare for their potential effects on our species' future. So should we be worried about Eta Carinae? Stephen Hawking's analysis suggests that while we cannot predict when this stellar monster will explode, we should absolutely be concerned about what happens when it does. The star represents the kind of existential threat that could end human civilization in an instant, and our survival might depend on taking such cosmic dangers seriously while we still have time to prepare. The next time you look up at the southern sky and see the Carina Nebula, remember that you're looking at the scene of a future cosmic catastrophe that could determine the fate of every living thing on Earth. Eta Carinae is counting down to an explosion that will be visible across the galaxy, and when that moment comes, we'll discover whether humanity was wise enough to prepare for threats that come from the stars themselves. If this exploration of Stephen Hawking's analysis of Eta Carinae has opened your eyes to the most underestimated cosmic threat facing humanity, make sure to smash that like button to support more investigations into the stellar dangers that could end our civilization. Subscribe to our channel and hit that notification bell so you never miss our latest coverage of cosmic threats and existential risks. Share this video with anyone who thinks that threats to human survival only come from Earth, because understanding stellar dangers like Eta Carinae might be crucial for our species' long-term survival. And let me know in the comments. If Hawking's analysis is correct and Eta Carinae could explode at any moment, should humanity be prioritizing space colonization as our ultimate survival strategy? How should knowledge of cosmic threats change our approach to civilization and resource allocation? What would you do if you knew that a stellar explosion could end life on Earth without warning? Drop your thoughts below and join our community as we explore the cosmic forces that could determine humanity's ultimate fate. The stars may be beautiful, but some of them are also the most dangerous objects in the universe, and our survival might depend on taking their threats seriously.